Welcome back to the second 40% of the Pappalardo Symposium, starting with our first-year Pappalardo Fellow, who obtained his PhD from Carnegie Mellon University, an expert in quantum field theory and high-energy physics. Duff Neill will be explaining to us effective field theory and particle physics.
Thank you. So there's this intuitive notion that we have that the large and small physics is somewhat independent of each other. When you go and play a game of billiards, you don't think about the motion of every single atom in the ball. And you don't take into consideration effects due to, say, the curvature of general relativity on the motion of your balls. All you think about is just the center of mass motion and perhaps the spin if you're a sophisticated enough pool player. And this intuition that there's all these other effects that we know exist but don't really affect what we're trying to do at a given length scale is formalized in the methodology of effective field theory. And to illustrate that methodology, I'm going to take an example, which is one that is enabling me right now to communicate to you, and that is a gas. And a gas, as a macroscopic scale, is sort of easy to measure. You know, there's the pressure of the gas, and then there's the temperature, and there's the density. And if I know those things about a gas, I've pretty much specified its macroscopic state. However, we know that deep down, on a very fine-grained level, there are all these atoms that make up the gas, and their interactions with each other can be exceedingly complex. If for no other reason, then there are billions of them. But not only can they be billions of atoms, the interactions between these atoms can be very complex, complicating how they bump into each other. And yet, somehow, all of these complex interactions give rise to relatively simple macroscopic behavior that we can see with our own eyes. We see the deflection of the needle due to the pressure of the gas. We see the mercury in the thermometer rise up and down because of the temperature of the gas. And this separation of scales becomes very evident when you just look at gas dynamics. And very long distances, the dynamics of a gas exhibit a very simple behavior, and that's just sound, what I'm using right now to communicate my talk to you. And sound, for every single gas, is all described by the exact same equation, the wave equation. And this, one could call the effective theory for gas dynamics, is just the wave equation. And all of that subatomic, nasty interactions going on between the various molecules in the gas are all parameterized by this number, the speed of sound in the gas. All of those complex interactions just get lumped into one effective number that I could just go measure. And the long distance effects are all universally described by the same equation. And this is a pretty profound situation which occurs in physics. And I will call this decoupling. In other words, the fine-grained details of the interaction of the gas don't affect the bulk motion of the gas, but instead the bulk motion of the gas is described in its own right by an effective theory, except for the parameters of that effective theory, which are set by the fine-grained details of the gas. And what's very powerful about going to the effective theory of the gas is, like I said before, all gases exhibit sound. And so there's a sense of universality that we are getting out of by going to this effective theory, which is, regardless of whether the gas is made of methane or argon, or even if I looked at a substance like mercury or water, or other liquids, they all exhibit sound waves. And that is revealed by going to this long-distance effective theory of the description of the gas that does not take into consideration all those fine-grained microscopic interactions except through the parameters of that theory. And we can summarize the logic of an effective field theory. The logic of an effective field theory is that there are some observed dynamics that we're interested in. And there might be some underlying physics that's sort of the deep down truth, if you will. And the underlying physics only serves to set the parameters of our effective theory. But the effective theory itself is just defined by the relevant macroscopic quantities we want to measure: the pressure, the temperature, the density. Those are the parameters of the effect. Those are the observables of the effective theory. And the underlying physics just sets the parameters like the speed of sound in that overarching effective theory. And this process by which the parameters are set is often called matching. And that matching process could be a calculation that one does if you know the macroscopic physics, or it could just be going into the laboratory and actually just measuring the parameters of your effective theory. Now I'm going to switch gears just a little bit, because I want to apply effective field theory in this powerful technique to collisions at the Large Hadron Collider, which has been in the news as of late. And it's been in the news because of the discovery of the Higgs. By colliding protons together, which are these complicated bound states of quarks and gluons, they, at very exceedingly high energies, the highest energies ever attained in a controlled laboratory setting, we've been able to discover this particle called the Higgs. Now, I don't have much time to actually tell you what the Higgs does or why it was important, but needless to say, it is sort of a cornerstone of our modern theory of the universe, the Standard Model. It sort of gives the gross features of the Standard Model, the underlying mechanism by which the Standard Model sets the stage for our universe is because of the Higgs. And here's a candidate collision, or a candidate event for the Higgs from the CMS detector. These two green lines are actually a pair of photons that were registered into the detector. And those pair of photons had a mass between them that was consistent with the mass of the Higgs. Now, all this other stuff that we see are the byproducts of the collision. Because as I said, we were colliding protons. And we were colliding protons. And these protons, like I said, were this complicated bound structure of quarks and gluons. And when you slam that complicated bound structure together, you get all this other junk, the remnants of the protons spewing all over your detector. And we would like to measure the properties of the Higgs. We would want to know its mass, but even more importantly, we want to know how the Higgs couples to the Standard Model. And we get that from how the Higgs decays in our detector. Here, this is an event with two gamma rays. So when the Higgs decays to the two gamma rays, that enables you to detect and measure how the Higgs is coupling to those particles. But you also would want to know how it couples to other species of subatomic particles, tau leptons, or say BB bar pairs. And when you start looking at these other decays, this mess will interfere with the measurement that you're trying to make. In other words, it will mimic, it'll be noise to the actual observation that you want to make about the Higgs and how it couples to the Standard Model. Now, in certain instances, we can perform a restriction. We look at very specific events, and by looking at very specific events, we clear out a lot of the noise. So if I wanted to know how the Higgs couples to two subatomic particles called the W boson, this, if I just looked at every event, would be lost in the noise. But if I look at a segment of events where there is not very much energy being deposited in the transverse direction, where my detector geometry is defined by the beam axis, I have this proton bunch and this proton bunch, they come together, smash, that's my beam axis. And I look at the energy that is moving perpendicular to that. If I just say, I only want to look at events which does not have a lot of energy in that perpendicular direction, that can clear out a lot of the noise and give me a better handle on the Higgs decays that I actually want to see. Now, here's where effective field theory comes in. There are many different scales going on here. First, there's the scale of the proton itself. It's sort of typified by what is called the Compton wavelength of the proton. And that's just sort of the size of the typical wave function of a proton if you just plopped it at rest. And the Higgs has its own Compton wavelength, but since it's a much, much heavier particle than the proton, there's a big difference between the scale of the Higgs and the scale of the proton. And like in the gas, there was a large difference between the scale of the observed quantities like pressure, temperature, and density, and the scale that actually forms the gas, the interatomic collisions. And we went to an effective field theory to describe gases, and that greatly simplified how we described the gas. Here, too, going to an effective theory where we separate the dynamics of producing a Higgs from the dynamics of the proton will enable us to get a handle on these types of collisions that we're conducting at the LHC. And now, to sort of step you through the process of how one would analyze this collision, I'm not going to actually use a image that a experimentalist might produce. Instead, I'm going to go to a cartoon called a Feynman diagram that we theorists like to talk about. And in a Feynman diagram, we might represent a collision as such, and out pops the Higgs. And here I took two protons, and as I evolved the movie forward, you saw them coming at each other. And as they come at each other, they begin to interact with each other. And as they interact with each other by exchanging particles, and at each link, these particles are just smacking into each other, like two billiard balls almost. They're just exchanging momentum and energy at each point. It rips apart the structure of the proton. And at the very heart of the interaction, at the very hardest, most energetic point, is where the Higgs will be created. And so if we focus in at that hard interaction point where the Higgs is being created, that happens at the very shortest length scales. And so it can be described by a theory, all on its own, where I don't have to consider the structure of the protons. That's much like how in the wave equation, I could calculate the speed of sound in a particular gas just based on the interactions between the various molecules. And so this hard sector where the Higgs is actually produced, that becomes a microphysics quantity in this collision, like the speed of sound in the wave equation. Now, each proton, as they were coming towards each other, they were well separated from each other in space and time up to the moment of impact. So the dynamics of each proton should be described in a sector all by itself. I don't have to consider how this proton is behaving when it's well separated away from this proton. I can just describe them individually. And that gets lumped into a sector which I will call the beam sector, and that's been factorized away. And finally, there can be very, very, very low energy radiation, which I'll call soft radiation, and that's the longest wavelength radiation associated with the collision. And it gets factorized away from the beam and the hard sectors. And finally, we draw a picture like this, where each proton and the soft radiation, the hard radiation, is been sort of factorized away from each other and described on its own terms. And to bring that back to the earlier part of the talk, this is very analogous to the exact same situation that happened in the gas. The speed of sound is analogous to the hard sector, and the form of the wave equation is very much analogous to these beam and soft functions. And in fact, we see the same type of universality that we saw in gases, where all sound in all gases is described by a wave equation. I could replace this hard interaction with a different hard interaction, and I would still have the same beam and soft functions. And so in a very analogous way that the form of this wave equation is universal to all gases, these beam and soft sectors become universal to all collisions that I'm taking place at the LHC. And this is a very powerful fact, because it enables me to measure one process that has some hard interaction and use that measurement to inform a different process that I would like to make a prediction about. Now, as I talked about earlier, we wanted to see how the Higgs decayed, and we wanted to isolate particular decay channels. And to eliminate noise, we had to constrain how much radiation events had moving in that transverse plane. And when you select events out like that, you're specifying a very particular type of dynamics to have occurred before your hard production. And so that strongly constrains the form of the beam and the soft sectors that you could possibly get. And in situations where you have this constraint on your transverse momentum, factorization becomes much difficult from the point of view of how people traditionally approached it. And my collaborators and I, we developed a new formalism to tackle factorization precisely in these instances where you're strongly constraining the motion of the transverse energy to these types of collisions. And this new factorization formalism has enabled very precise calculations to take place at the LHC. So here's a plot made by a professor here at MIT using this formalism that my collaborators and I developed to describe these types of collisions. And each band in this plot is an increasingly more accurate prediction for the type of how the production is going to be performed. And along this axis, there's a cut in the transverse momentum. In other words, this just specifies how much energy you're allowing to go into that transverse region. And on this axis is the cross-section, which is just sort of the probability to see an event given the fact that you've made this transverse momentum cut, this vetoing on how much transverse energetic radiation there can be. And the new factorization formalism that my collaborators and I developed enabled for these sort of increasingly accurate bands to be calculated. Before, it was very unclear how you would systematically include terms in your calculation and have an accurate estimate as to how big all the terms are going to be and how they all fit together and sum together. And if you don't understand systematically how all the terms of your calculation are being put together, then it's very hard to say that I am calculating more and more accurately as I add more and more terms. And so with this factorization formalism, we've enabled very precise predictions to be made in these sort of transverse momentum-dominated collisions. And so in conclusion, I would just sort of like to trumpet effective field theory because it is a unifying approach to physics. I started out talking about gases, and I moved to talking about particle collisions. But the ideas that I used to analyze the gas and the ideas that I used to analyze the particle collision, those were the same ideas, the same type of thinking. And effective field theory is essentially just trying to exploit the separation of scales to tackle what is relevant to what you're observing. And it provides a very powerful paradigm to find universal behavior. The wave equation is a great example of universal behavior. And effective field theories help uncover this type of universal behavior in systems that you might think were otherwise unrelated to each other. By going to an effective field theory, you often find that these microscopically unrelated systems macroscopically behave exactly the same way. And finally, when you apply these effective field theory techniques to particle physics, it yields very precise and controllable predictions, which is important for furthering the research program at the LHC. And lastly, I would just like to thank Neill and Jane for allowing me to continue my studies of effective field theory here at MIT, which is a great place to do it.
Apparently, you use effective field theory on a very difficult problem, the interaction of protons at CERN. Mm-hmm. I assume you start at a much smaller set of experiments to determine this. I would assume if you looked at other interactions of particles, you could have done something similar, but perhaps empirically proved that whatever your conclusions were correct?
Yes. So, well, I guess there's lots of instances in which you can apply the paradigm of effective theory if you just want to test the paradigm of effective theory. So one example that I love to cite about sort of the range of length scales for which effective theories are good for is that there's a problem in astrophysics about the binary in spiral of two black holes. There's an analogous problem in particle physics, and you could call it the binary in spiral of two heavy quarks. And both of these can be tackled through a set of effective field theories that are very much related to each other, even though naively you would think, what does a quark have to do with a black hole? They're very different objects. Now, with the quark instance, we actually have lots of information. We've done lots of measurements of bound states of two heavy quarks. And so we understand that system very well. In the black hole instance, well, hopefully one day LIGO will measure two in-spiraling black holes. And maybe even more hopefully we might have LISA fly. But the set of techniques that one uses for these heavy quarks immediately applicable to this binary in spiral problem. And the confidence that these effective field theories techniques have given us in the instance of applying it to these quarkonia states really help us to have confidence that when you apply these techniques describing the binary in spiral problem, that you'll have a very profitable sort of theory output that hopefully that LIGO will be able to measure something that you can then compare against. So, I mean, that's an example of sort of two very disparate situations where effective field theory reveals actually a deep underlying connection where if you looked at it from the face of it, black holes, quarks, you wouldn't necessarily suspect that there is one because you are focusing too much on the microscopic physics and not enough on the effective theory.
Very good, thank you. Other questions? I want to ask about the way in which the calculation progresses, not at a technical level, but in terms of what you start with and what you want to get out. I think I understood in the proton-proton collision calculations, you're trying to simplify a calculation in order to break it up into chunks that are manageable so as to calculate a collision cross-section which can then be measured and therefore give a test of the theory. But you could imagine, and in a way that's like saying it's too complicated to calculate all the collisions of molecules in a gas, so I'm going to reduce it down to calculating a speed of sound, go measure sound waves, see if they obey the wave equation, and then measure the speed of sound. You also, though, could say, well, I don't know what this gas is made of. I'm going to go measure the speed of sound and try to learn something about the physics at that microscopic level. Which approach is the right one, or are they both right in different circumstances?
They're both right in different instances. I mean, it all depends on the question you want to ask and what you can actually measure in the laboratory. Sometimes measuring the speed of sound is easier to do in the lab. Sometimes it might actually be the microscopic interactions. And in certain instances, what is interesting about the speed of sound is that the problem is sort of inverted. It might be somewhat difficult to calculate the speed of sound, but it's very easy to solve the wave equation. If you want to solve the proton's structure, that's a very difficult problem. Relatively speaking, calculating that hard interaction is easy compared to solving the structure of the proton. So it's easy in this instance to calculate the microphysics quantity, the hard interaction. What's hard is actually calculating the large scale structure, which is just the structure of the proton in the collision. So it's sort of inverted from the gas dynamics problem, where it was easy to solve the wave equation, but much harder to figure out what the speed of sound is from the microscopic dynamics.
Does that mean that at the LHC we should perhaps cease focusing so much attention on the Higgs itself, but use the Higgs as a probe of the structure of protons?
Well, I mean, the answer is that at the LHC, they use very similar collisions that have that happen much more often to probe the structure of the proton. So right now, there is an ongoing sort of program at the LHC to help improve our understanding of the structure of the proton by measuring processes where you're not necessarily producing a Higgs, but you're producing a Z boson or a pair of leptons, which much more readily get created at the LHC than a Higgs is.
Great. Well, thank you very much for explaining all about the Higgs and the effective theories.